Hello, algebra people. Here is your video on an introduction to functions. We're going to review some stuff you might be familiar with and possibly add some new terminology here. So you should have 3 sheets taped into your notebook, and I'm going to be going through these sheets, filling them out with you. Make sure you listen carefully so that whenever I come back, we can do all the classwork successfully together. So first of all, let's just go over the definition here. You've heard the definition before, but it's always good to review it. So a function is a relationship between 2 variables. The variables you're most familiar working with are x and y, but they will start to be different because we're going to do them in context. So then they will change depending on what context we're in. So each value of the first variable is paired with, now here's the key, exactly one and only one value of the second variable. Now keep in mind here that a function is a type of relation, and they are different from one another. So a relation is a mapping or pairing of input values with output values. Now our input values are what we're going to call our domain, a word you're probably familiar with. Output values are what we're going to call a range. So if I have a relation, just think of like any kind of relationship. I'm taking 2 different things, inputs and outputs, and I'm mapping or pairing them together in any way. There's no rules. It doesn't matter how I do it. For a function has rules. Whenever you map these things together, every input can only go to one output. Whereas if I had a relation, one input can go to 2 different outputs. One way that you can represent this is, let's say I have a set of all the relations in the world. This is a massive set here. Within that set is a subset of functions. So a function is a special type of relation, and it has a rule. Every input goes to one output. This is kind of like saying every square is a rectangle, but not every rectangle is a square. So functions are more specific because they have rules. Now, we're going to be representing functions 4 different ways in this class. So we can do it with a graph, which obviously is called graphically. If you represent it with a table, that's called numerically. With a real life situation, that would be verbally because you're doing it in words. And if you have an equation, that would be algebraically. That's if you actually have like y equals something or f of x. Now, function notation that you're going to need to use, which you're already familiar with, just a reminder, instead of always saying y, we might sometimes say f of x. They are interchangeable, and you should be familiar with using both. So we're going to do the first way here graphically. A graph represents a function if it passes. Now try and think for a second here. You've probably heard this rule before, but if you're looking at a graph of something, there's a certain way to decide if it's a function or not. So for example, let's say I had this graph right here. If I were to ask you, is that a function or not, you might be able to decide. So try and decide right now what you think it is. If you decided it's not a function, you're correct. And the reason why is you might have used something called the vertical line test. And the vertical line test says that an imaginary vertical line will intersect a graph at no more than 1 point. So if I take a look here, now remember, the lines I'm drawing in red are not actually part of the function. These are those imaginary vertical lines. If I hit this function, or if I hit this graph at more than 1 point, it's not a function. So like right here, I'm hitting once, I'm hitting twice. Pretty much anywhere you look, you're hitting twice. So because I'm hitting more than once, this is definitely not a function. And just keep in mind, we usually use VLT to abbreviate vertical line test because it's long to write. So it fails the vertical line test. There is, however, 1 point where it passes a vertical line test, and that's if you go right on the y-axis. I do pass the vertical line test right there. However, if it fails at one spot, then the whole thing fails and it's not a function. So I'm going to draw a couple others here. Don't stress out too much about making these exactly like mine. Just make sure you have the general idea. All right, so this is what I drew here is a cubic. We'll be doing those a lot. This looks kind of like a parabola. Let me scoot up a little bit here. Next, careful when you draw this one. Go straight up here, across, diagonal. And let's do one more like this. Okay, I want you to pause the video and I want you to decide if they're a function or not. And if they're not a function, make sure you clearly show where it's failing. So make sure you actually pause the video and do this yourself so you're actually thinking, and then unpause it. So you should be back and you should have decided for each one what you think. So for this one here, this is definitely a function. Every imaginary vertical line is only hitting once. Every x only goes to one y. No matter where you go on the x-axis, there's just one y that goes with it. The next one is also a function because every input has just one output. It passes the vertical line test. So graphically, that's why it is a function. Just be clear that even right here, I didn't draw it perfectly. It might look vertical and it might look like you're hitting more than once. Parabolas do go down and out forever. It just goes left very slowly. So this is definitely a function. This one right here, it passes all these places. There's only one time it hits. But right here, if I draw a vertical line at this x value, I am hitting many, many, many times. And actually, the amount of times you're hitting is, you can't really count it. It's infinitely many. So right here, this is a phrase we're going to say infinitely many points. We'll say that phrase a decent amount of times this year. It's a huge word you use in calculus, infinitely. So it fails infinitely many times right there. This right here is what you'll see in pre-calculus. It is a sine wave or a sound wave similar to that. This definitely passes. Now what I want you to do here is you make up your own example of a non-function and then show where it fails. All right, we're going to move on to the next type with a table. So tables are really just ways to organize ordered pairs. You have a bunch of ordered pairs that you want to put together on a graph, you put them in a table. It's a nice way to organize it. And we're going to represent functions and non-functions or relations in this way. Go back here. And one thing I meant to say is one word that we're going to be using is the word continuous. So make sure you write this down because we're going to do the opposite of continuous in just a moment here. All of these graphs here are continuous because you can draw them without lifting up your pencil. So draw without lifting pencil. It's usually a smooth curve. It doesn't have to be though. I mean, these weren't smooth curves here, but that is continuous. So that's just a word you're going to need to be familiar with. Okay, back to tables. Whenever I have a function here, every x, remember, is paired with exactly 1 and only one y value. We're going to use some data that might be slightly dated because I don't think he's playing anymore, but since he's one of the best Celtics players in history, we can go with it. Kevin Garnett. So we have tables representing the average points per game versus his age for his first 9 seasons. And we're going to decide is this thing a function or not. So in this case, age is represented by the variable a, and p is going to represent points. So when Kevin Garnett was 20 years old, his rookie season, he only got an average of 10 points per game. When he was 21, 17 points per game, then 19 points per game, 21, 23, 22, 21, 23, and when he was 28, he actually kept increasing, and you got 24 points per game. So what we want to do is quickly plot this here so that we can visually see this. Age is our independent x, and points are our dependent y value here. And I'm just going to do one of these here, and I'm going to call this 20, 22, 23, 24, 25, 26, 27, 28. And for our points, I'm going to go by 2s, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. You can do a different scale if you want, but pause the video and get this thing plotted and then come back. Your graph should look something like this, depending on your scale. Now, quick glance at this is going to immediately show us that this is a function. It's clearly passing the vertical line test. If you look here, every single input, your x, goes to just one y. It's not like when he was 22 years old, he had an average of 19 points per game, but also 24 points per game. Like, you can only have one average point per game whenever you're a certain age. So what we're going to say is, now it's very important that you can write this correctly. Just remember, normally if something's a function with our regular old x and y, we say y is a function of x. So I'm just going to take whatever represented y, which is points per game, is indeed a function of, and my x is age. The points per game are a function of his age. Now, another way of writing this, instead of saying y is a function of x, we sometimes say y depends on x. That's an S. So in this case, we would say Kevin Garnett's points per game depend on his age. His age doesn't depend on the point per game. The point per game depends on how old he is, his age. So now just keep in mind that, like, right now this is an upward trend, but this upward trend is going to stop at some point when he retires, or at some point you just get so old that your body cannot continue performing at that level and it will go downhill. Another thing to keep in mind is whenever you do your homework, at times you're going to have to write, or at times you'll see a table written in a set notation, which I will show you here. And it's only done for something called a discrete function. And a discrete function is different than continuous function, which you wrote right there. So continuous is when it's a smooth one line that you draw without lifting your pencil. Discrete is whenever it basically looks like a scatter plot. So it kind of looks like a scatter plot whenever you put your points on it. You don't connect your points. So this is a discrete function, and a discrete function can be written as follows. So for this one, you would put like 20, 10 in these curly brackets. Sometimes they're hard to draw at first, but you'll draw them enough, you'll get used to them. 20, 10. And then we have 21, 17. I'm not going to write all of them, but just so you get the point, it just keeps going. You put every single ordered pair in this curly bracket set notation, and you only do this for a discrete function. So now what I want to do is take this same data and flip it. So instead of doing age versus points, let's do points versus age. So take a second and reverse these tables, put the same exact ordered pairs, but flip the x and y, and then come back. This right here is a table we'll be dealing with for this example. What I want you to do next is go ahead and plot the data, just like you did last time. Don't spend 20 minutes on it. Do a quick sketch, put the scale however you want, then come back again. This is what you should be looking at once you've plotted this. I'm going to stop the video now because I'm going to get cut off, and then I have a little bit more in part 2. So as soon as you're all caught up, go to the next video.